can play around with that a little bit more. But right now, the way it works, these are sorted. These numbers down here at the base of each one are actually the scores for that thing. So this one, it's a little bit surprising. This one's the best score. Who's that? Well, you say, who's that? I can tell you who that is. Ta-da! It comes up here. Christina Brown, very good. Mr. Hardy's, I need my glasses. Meekin Stewart, Cameron Stewart. And there's all the data, you know, height, weight, load they carry. 338 pounds. Oh, they were the heavy one. No wonder they won, huh? So they're the winners with a score of 166. They pretty much blew it away. And this thing, this is supposed to be the value of, you know, when that works is by how many people pick it. So that's just for fun. Well, the whole thing's just for fun, actually. But and if you pick play. Oh, and oh! Where's my audio here? What's it say there? Not working? Shoot. It says I can't see. Oh, it must be on the other side. Where the heck's the audio jack on this thing? We went through this one time before and got it wrong. That's probably wrong. What's it say? Some of the mime. Oh, yeah. Okay, whatever. I can't read that anyway. Whoa. And there should be audio with this, but it probably is not going to come on in this situation. Oh, it's probably turned off. No, it didn't. It's not picking it up for some reason. Maybe I've got to play a game here. Oh, it won't let me do it. What's with this thing? Oh, shoot. The best part's the scream at the end. Ah! No, it should be this. Oh, no, we don't want it on. Oh, well, that's all right. Whatever. But you get the idea. So you can, unfortunately, we should have had the camera set at a little bit higher resolution. You can still blow it up, I guess. How do I get full screen on this guy? Shoot. That's not what I want. How do I get full screen? You don't know. A lot of help you are. File source. It seems like... Oh, that's because it's running... shoot. Okay, never mind. This isn't going to work. MIME settings. Oh, well. When you can download it and do whatever you want. You can download them. I put them all up on the temp server too, if you're familiar with that. And if you're not, read that email I sent this morning. And then you can take this video. It's unfortunately not quite the highest resolution. So when you blow it up, it'll be a little bit fuzzy. But you should still be able to, you can frame through it, you know, right when it finally fails. And you should be able to get some idea of which member failed first, you know, whether it broke at an individual member, or you can usually see them tip some of them, or this one's still got a ways to go. I don't know. See if we can speed the process along here a little bit. Da-da-da. You can also speed it up. And will he do it? We've got to get some more weights. I must say, this somehow, I think it was the allowing balsa wood, perhaps. Oh, it was at the base, wasn't it? It was the base that finally did it in. And you can bring it back to life. Oops. Whoop. Let me see if I can. Well, okay, I can't step through it so well. Why not? You should be able to frame through it. Ah! Okay, we're one frame off there. Up. Up. Oh, well, I can't get it. You can try to capture that frame where it actually fails. At 30 frames per second, you should be able, even at that kind of slow speed, you should be able to see it. And then you can make some statement about why that member failed, or something like it broke, it was weak, or something to that effect, and get that all put together in your report. What else should we say about these things? Oh, we have never had such high weights. I don't know. Yeah, I guess I started to say, I think it was the balsa wood maybe that did that to us. But how come this is so loud? But anyway, I guess next year maybe we'll have to buy some more weights. Or change the rules. We'll have to make them more stringent rules, right? Cut it down to 3 ounces or something. I don't know what to do. You're going to build it. It's got to be 6 feet high and 2 ounces. Build it out of toothpicks. Build it out of straws. Something really weak. Okay, well, build it out of concrete. How about that? Whoa. And weigh 4 ounces. So, let's see. We were supposed to do something today with concrete. Where am I? I'm supposed to talk about this. We had been... Oh, that means I don't even have my clicker. Man, this is primitive. Okay. Well, you probably worked through a problem already. You may have even done it yourself, the analysis problem. So we can probably get through this pretty quickly. This always fascinated me. Just this technique, the idea that you've got this little similar triangle up here, and then this big one that's kind of a I mean, it's like a philosophic concept, don't you think? I mean, this really exists, but this dashed line is just, it's just so creative, don't you think? I mean, the idea that you could pull that dimension down, you add these 2 dimensions, it becomes this giant triangle that doesn't really exist, but you use this sort of figment to work out all this equation, because it's based on this ratio. C is to D, this to this. So the D is the leg of this giant triangle, and there's the base of it, which is then that number there. It's that plus that plus that. That becomes that whole thing. So then you have a ratio of triangles. It's amazing. I mean, who was this? The Greeks that came up with ratios and triangles, or maybe the Egyptians? No, let's say it's the Greeks. And we still, I mean, basically use these concepts today. And amazing, huh? Anyway, to do concrete design, which, by the way, did you know, I should post this article. It was discovered back in the 80s. There was a French researcher in concrete that discovered, and this was hushed up, you don't hear this just everywhere, that the pyramids in Egypt were made out of concrete. They're not cut stones like people try to lead you to believe. And and the myth has perpetrated for millennia, right? I mean, how many? 3 or 4 at least. And it's not. They're concrete. And this guy figured out not only that they were concrete, but where they mined the ore, what the formula was, how they put it all together. That, this whole thing, you always see pictures, oh, it was such a master feat to lift these big blocks way over their head, and up. No, they just cast it. They buckets, a bucket at a time, and all up there. And he the part of what kind of proved it is he found a couple things that were cast in there, like a toothbrush or you know, different things that obviously weren't in the natural stone. A human hair, I think, supposedly. I don't know. Well, maybe not. Because you'd think that'd decay. Maybe. Well, I don't know. A lot of things don't decay. Mummies don't decay. Anyway. Yeah, toothbrushes. So, you know, apple cores, everything was in there. And then the ultimate proof, he wanted to take a couple blocks and break them apart. And the Egyptian government, when they heard this was going on, totally forbade him from doing that, because, of course, it would make, you know, the myth, it would shatter this myth. Although it's still, I think it's even better that they cast it. I mean, that's kind of cool. But no, they wouldn't let him do it. But this was not in just this wasn't in National Enquirer, I read this. This was in the American Institute of Concrete, ACI, American Concrete Institute, whatever they are. AIC, ACI, I can't remember now. Whatever. I'll post that. That would be an interest. I'll email you that article, so you can pull that out at the next party you're at and say, hey, did you know? Recent news here. Well, anyway, but they didn't have these formulas to work with. They didn't reinforce their concrete. How do we get off on them? Anyway, A, here we go. This is the formula for A, which comes from, we talked about this already, didn't we? I better go on. But you substitute A, this is the formula for A, and you substitute that into here, which is the formula for C, and you get this, and then you have two formulas for C. This one from the similar triangle for C, this one from the relationship of the forces. This is a force relationship, this is the strain relationship. So you equate the strain and the force like this. This one goes here, this one goes there, and then you solve for rho, which is somewhere. There's rho. And this then, because this is set up, this is defines the balance situation. This is failing, and this is right at yield, and this is the yield strain, the steel yielding, and this is the concrete yielding. So this diagram is what defines it as balanced. That's that diagram right there. If I put that on an exam and said, what is rho? When you see this, you should say, oh, that's rho balance, because that's right at the fail. That's a definition of failure strain for concrete, and this is the definition of the. See, isn't that interesting? That the definition of failure is by strain, really, not by stress. It's how much it's being crushed that defines the strain, that defines the failure. Yeah, that's kind of interesting. Anyway, so then that is the balance condition, and this balance is different. You can see, look, here's F prime C and Fy. So every time you have a different grade of concrete, there's a different balance. And that's kind of interesting to know, because the amount of steel you're going to be allowed to place in the beam is dependent on what balance is. So the amount of steel that you can place in a concrete beam depends on the grade of concrete. The higher the grade of concrete, that's the grade of concrete. If I go from like, well, kind of a trashy 2,000 or 3,000 KSI concrete, or 2,000, sorry, PSI concrete, up to maybe a really spiffy 10,000 PSI concrete, that means I can put more steel in it. This number will get bigger, this will get bigger, and this, where is it? Oh, right here. That's maximum. This is balance. This is maximum. So the higher I go here, the concrete, watch this number. Well, let's go down to 60. That's a balance condition, 0.01, 3, 0.016, 0.02, wow! But see, I'm 4,000, 5,000, 0.02, 6,000, 0.028. So that number, the balance is going up, which would allow me to put more and more steel in it. So as you get better grades of concrete, the concrete gets stronger, and you're allowed to put more steel in it, so that the whole beam gets stronger. So the result is, of course, the cross section can get smaller. So if you're designing a beam and you specify something like 2,000 psi concrete, you're going to have a big beam. That's going to be a chunk of concrete. If it's important to have a small cross section, then what you're going to need is a higher psi. Of course, the concrete's stronger, but even more important, you're allowed to put more steel into it then, so the whole thing gets stronger. It's not just the fact that the concrete's stronger, because really the concrete's only acting up here. It's only half of the, it's way up here at the neutral axis. It's a pretty small amount for the whole section. Anyway, but the price you pay is money, because the stronger the concrete is, the more expensive it gets. It gets more expensive because it probably has a little bit higher percentage of cement in it. More cement, less sand and stuff. It may even have some admixes to get the strength up that high. It may have a super plasticizer, a water reducing agent. Remember the strength of the concrete's controlled primarily by the amount of water in it. So to get that water down, to reduce the amount of water, you're going to have to maybe do something else to prevent it from getting too stiff. You may have to pay for an admix, a super plasticizer, or something that allows it still to be workable at a lower water content. Well, that just increases the price of the concrete. It makes it better, but it's a little bit more expensive. So this may be, and you can go higher than this, 6,000, 7,000, 8,000, 9,000. You can get up, you get up close to 10,000 psi concrete, and this is just not your average mix. I mean, that gets to be to the level where it's hard to do on site. It's hard to get a truck to deliver you that quality kind. Not that you can do it, but that's going to take more quality control and everything to really ensure. In a casting plant, it may not be so difficult, pre-casting plant, because for a couple reasons. One, you don't have the transport. You can mix it and dump it right into the form pretty quickly. You don't have to wait an hour in between for the truck to get there and the other things that go on. You can also, in a pre-casting plant, you can usually deal with a much stiffer mix. You're probably not going to have to pump it, or you're not going to have to work it in the same way that you would on site. You can put it into a form and fairly dry at a lower slump, at a lower water cement ratio, which will make it stronger. So you generally can get higher strength concrete in a precast plant, which is an argument for using man, what's happening? I'm echoing. You can usually get, it might be a argument for using precast members, which I don't think are used a whole lot in this country. I mean, it doesn't seem like, we do mostly cast in place stuff. But in Europe, in Vaterland particularly, they do primarily precast. Yeah, what's going on? My batteries are surging or something. Be electrocuted. I'll start to glow. Smoke will come. Sorry, I'm under control. Too much coffee this morning. I had 3 cups. Wow. Okay. In Germany, in Europe in general, I think they do more precast. I don't know why they do that, and they truck it around, and you have special details for it's erected. With it's just the way you work, the way they work. We don't do quite as much precast, but the advantage is you get better quality concrete. You get higher strength at a better cost, at a probably cheaper than you would otherwise. I don't know. Be interesting to somebody can figure that out. Why we don't do that here? Okay. Woo. So, I guess we're up to this. How to do rectangular beam analysis. And this, I guess, did you cover this in section? Did you cover it in section? Everybody do this already? Oh, good. So we'll just kind of, this is a review then. All right, a review. Here we go. Analysis means what? You've got all these parameters given, B and D, and, well, you can figure out C, and the steel's in there. You think, well, what's the point? Oh, well, you want to analyze it to see how strong it is. You want to find maybe Mn, which is the strength of the member, or once you get Mn, you could calculate what its capacity is. This would be, Mu would be then in that sense a load capacity, how much load it can carry. This is kind of an interesting difference. Whoops, hey, where's this button going? This is the strength of the member, as you know, from all the pieces. This is the load side. This is, and these two numbers you equate somewhere. See? Well, with a phi on it. You want the strength to match the capacity, right? You want the thing to be as strong as the load it's got to hold. This side of the equation, this is the where the loads are coming from. This is WL squared over 8. This side of the equation is based on this internal couple here. Where is it? This moment is equal to, here's this force times this moment arm. That's what that is. That's the moment arm. So it's simply you could take this force to there and this force to there, rotate them about this neutral axis. You could rotate them about anywhere, actually. But why would you do that? It's more trouble. You can sum, to get the moment of this internal couple, you can take this force rotating about that point right there. And if you do that, then this force has no moment arm. It would be 0. So you can take, for the moment here, the couple, the moment of a couple is always the force times the distance between them. And these two, T and C, are equal. They've got to be equal, right? This is push and pull. If they weren't equal, your beam would start going or something. I mean, crazy. So these two have to balance. And the moments, of course, then balance because they have the same moment arm. So this rotation and, I mean, either way you figure. So you could say C times this distance or T times this distance. Either way, it's going to be the same. This is probably simpler because, I mean, look at this equation. Oh, my goodness. You got all these numbers. This is a little bit shorter. So here you got A. Oh, yeah, this is pretty easy to figure out. You can get A by beta times C. Well, that doesn't sound very easy. Well, you can get it from this equation here. Here we go. This was derived a little bit earlier from the dimensions of the stress block, right? I think, or something like that. No, from the couple. I can't go backwards, so I can't show you. Anyway, that's a formula for A. It has AS in it, right? Because when you think of that, well, that makes sense, doesn't it? Because if I increase this, right, I stuff more steel into it, then the compression in the top has got to balance it. So in order to maintain that T is equal to C, C's got to get bigger. If I stuff more steel in here, this is going to get bigger. I mean, potentially, it's the strength of it. It will get stronger. So at that full load, this would have to also be bigger. This would have to go down. The only way this can get bigger is for this dimension to get bigger. So that would mean A would increase. If I increase AS, the stress block gets bigger. They're linked. You can imagine you stuff it in, gets bigger. Take some out, it's smaller. And the neutral axis shifts up and down. So as you put more steel in it, this neutral axis comes down. Less steel will go up. But also it affects the strength there. The strength, of course, is based on that number there, right? Times the moment arm, but that's a big part of it. So anyway, this actually isn't changing very much. Whether it goes, going up and down is not really that big a difference as opposed to the amount of force that would change there. So this is in the changing of this, that would probably make more difference. Anyway, okay, so you get A, you plug A into there. You already have these dimensions, right? That gives you right away Mn. Mn, you can equate, this is the strength of the beam. If you put the safety factor on it, then you can equate it to the load capacity. And this also has a safety factor on it, remember. This has got the gamma, this has the load gamma factor on it, and this side has the phi factor. So this is the fully factored equation here that equates the loads to the strength. Then you can, if you want to find actual capacity, this is already known, right? Because you've got the dimensions of this beam up here. And then you could solve for this. And this would be this is the live load. This would be the live load capacity. So, oh, hey, look, that's what it did. WL squared over 8, and subtract off that, and you get what's left by that. So that would be how much live load you could put on the member, which might be an interesting kind of thing to know. All right, so to blow through an example here. Here's one. Everything's given, right? 4,000 PSI concrete, 60,000 PSI steel. This is the yield strength of the steel. This is the failure of the concrete, actually. 3 number 8 bars. There they are down there. How thick's a number 8 bar? Good job. 1 inch. It's an eighth, right? That's 8/8 of an inch. So that's a 1 inch diameter bar. Not counting the little bumps on it, I don't think, or something like that. Anyway, here's our picture. Strain, okay. This is going to be at ultimate. Now this is a little bit interesting here. This is not necessarily balanced, right? This is at ultimate because whenever you see that number, the concrete's failing, okay? So this diagram represents the ultimate strength. But look at this. What's with this? Little, what is that? Epsilon? Huh? Yes, that's the strain. That's the strain in the steel. Not necessarily the yield strain of the steel. The steel may, well, wait a minute, what am I saying? Maybe beyond Fy, right? No, it couldn't be beyond Fy. Oh. Yes. The strain could be beyond the initial yield, I guess, because the steel has to yield first. But I have to think through this a little bit. Why is that like that? Well, anyway, this would represent failure. I think that could be. Yeah, I guess that is. I'm trying to. If we put more, if we have, now the steel should yield. If this is at failure, this might be beyond the strain for yield, I guess. Well, that's kind of strange. At any rate, you don't need it. If you go beyond, the reason I pause is because if you go beyond the yield strain for the steel, then it's already, once the steel yields, then that defines failure. So what would maybe happen is before you'd reach that number, this would reach the yield strain, but then that would kind of be the end of the strength of it. So okay, well, whatever. This is the setup of the force stress blocks. If I want to check it for the row to make sure I'm within, I've got to be between a maximum and a minimum, right? This maximum, we could have, where was that? What did I just have? Grade 60 and 4,000. Here's 4,000 PSI and 60. This is row balance, 0.0285, and this is row max. 0.75 row B is row max, 0.0214. This number, 0.5 row B, is just kind of a target number used for design. That's what might be a good number to have. So that is max 02, I'm sorry, this is balance 028, and max is 0214. So to calculate it, this actually does the calculation. Hey, get the right answer, 0285. So that's with the formula. And the maximum is 0.75 times that. There's the 0214. The actual is just simple AS over BD. There's the BD. 0113, I forget what was 0.5. 14. Okay, so this is actually a little bit below 0.5 rho B. So it's a little bit, not so much reinforcement. Could have put more in there, but it may be enough. A lot of times these dimensions, 20 by 12, will be determined architecturally. You know, it may be like for the whole building, you're using a 20th depth for the beams, because it's nice to keep a consistent depth on the beams. And you might even keep a consistent width because they may be matching up with columns. So the depth and the width may be set, and you'd control the strength of it, you know, how strong it needed to be by the amount of steel that you put in it. So a lot of times these numbers will be even, 20 and 12. I mean, somebody's got to build some formwork to match those, right? But the amount of steel and the placement of the steel doesn't necessarily have to be. Well, there are little chairs underneath here. I guess they're even increments, and you have to have an even number of bars, but it could vary the strength anyway by that. What's not shown here, and I guess we talked about this before, is there's a stirrup in there, a little kind of U-shaped thing that resists the shear force. Okay, so getting back to this guy, here's the minimum amount, 200 over Fy. This is in there to prevent that initial crack propagation, and that's pretty low. That's way below this. So our number here is definitely between that, so it looks like we're good. Then you can go ahead, we want to find the capacity of it. You simply plug the numbers in. This is the formula for A, for little a, the you know, stress block dimension there. And there's the steel, the amount of steel. There's the grade steel. This 0.85 is a constant that is applied to F prime C because it's used in a beam. So there's those. This is the width of the beam, and that's in inches, 3.49. You can think that's a number that you can think about, right? It's not very big, but at least it's a number, 3.5. So, okay, it's about like that. So you're saying, okay, that's how much concrete is effectively acting in compression. If you got a number like 0.02, no, I don't think so. That would mean you don't have a little sliver of concrete acting? Come on, that makes no sense at all. Or if you got a number like 25. What, 25? The beam's not even 25. How can that be? It's totally impossible. So you can at least think of this number and see that it's sort of possible, right? It's like that. The beam's 20 inches deep, and it's up there at the top. So you kind of get a, all right, it's not a real big, that's because it's not real big because there's not really so much steel in this beam, right? It's below half row balance. Anyway, so from that, you can then calculate the moment arm. Goes from the center of that stress block down to the steel, so that's what that number is, the moment arm. There's the force T. T times the moment arm gives you this moment. This is the strength. If you put a phi on it, right, there's the factor. Now this would be phi mn. That's all I changed here. I just stuck a phi in there. Phi mn is equal to, or, you know, I mean, equal to or greater than the required moment from the loads. So there's the required moment, the design moment, I guess it's called. There's phi. There are all the other numbers, and that gives you in inch pounds. Be careful of the units. This is in inches. Everything here is in inches, right? That's in inches. That's all in inches. And that you've got to put in. You might be tempted to, well, it doesn't matter. Don't be tempted. Just put that in inches. Yeah, it's the only thing you could put it in, for heaven's sakes. I don't even know what it would be in feet. So that comes out in inches. pretty big number. If you divide by 12, and 1,000, knock off the zeros, you'll get kip feet. That would be a little bit more useful number. This you could take then, and that mu, how much time do I have? Oh, maybe I won't do it right now. And run through this then. You could put this, if you wanted to know the live load, you could subtract off the dead load. You know how to do that? Maybe that would at least be worth mentioning on the scheme of things. You know how to get the dead load of this? If you have the, no, not with that one. Try this one. Oh, much better. Man, okay. Try this one. Ah, just right. Okay, area over a conversion for inches to pounds, and then the density, 150, which is pounds per cubic foot, right, equals pounds per linear foot. So if we took the area of this 20 times 12, right, we've got is that right, 240? No, that would be, yeah, that's right. Over 144, are you figuring this out? Yeah, good, very good. Times the density, this is the density of concrete. This number, concrete by itself is usually about 144. It's pretty consistent at about 144, but they use 150 generally in practice to account for the steel. You got a little bit of steel in there, so it's a little bit heavier. So that's kind of a pretty close number, which comes out to be 250. Really? Yeah, because these are almost the same. Okay, a little bit up. Pounds per linear foot. So that's how much it weighs. The beam itself is weighing that much. You could stick that in here, put the safety factor on it. This is the gamma factor for the dead load. So you're subtracting that off, and this would be, and the moment over it, span, everything. This, let's see, is going to go in and, well, you have to make sure these numbers agree, right, that you get it all in the right units. If this is in foot-pounds, then maybe that ought to be in feet. This is in a feet, then everything would be in feet. That would be a smart thing. And then you'd get your load capacity in PLF. Nice, huh? Okay, how about a slab? Oh, yeah, maybe I should look at this on the board, too. The one interesting thing with slabs, what you do to analyze a slab, I mean, you could pretend it's a super wide beam, but that would be a real nuisance. I mean, you'd have these wide numbers, and I don't know, somehow it just seems more trouble. If you take instead a 1 foot strip out of it and imagine that it's a bunch of 1 foot wide beams sitting next to you, I mean, and calculate everything based on a 1 foot strip. That makes the load, because all the loads come out in PSF, that makes it very easy to deal with the loading. It also then takes the length out of the equation. You can make it whatever length you want. I mean, you know, the width of the slab, or however you see that, not the span. The only thing that is a little bit tricky is you've got to define what the steel is per foot. And you can imagine if these bars were exactly a foot on center, well, that would be beautiful. Then you could have 1 bar per every 1 foot cut, right? You know, if you're 1 foot strip, you'd have 1 bar in there. But if the bars aren't a foot on center, well, then you're going to have to adjust it a little bit. If they were more than a foot on center, like in this case, 18 inches, well, if it's 18 inches, then you have less than 1 bar per foot, right? It'll be less. So if 1 bar, what bar do we have? Number 8, is that 7.6 or something? Where's this? What's the area of a number 8 bar? 7.9. Okay, so if I've got the area. I want to find AS, right, per foot. 12 inches. Then I'll take the area of the bar, right, the area of that number 8, and then I have to spread it out for 18 inches on center. I'll have to spread it out, so it would be 12/18, right? That would reduce it. That's going to make it smaller. That would be 0.79 times the 12/18. It's probably up there somewhere. Oh yeah, there it is. 0.527, whatever, and that would be inches squared per foot. Right? That way you can, and the best way to think about it, I mean, just think about it logically to get that equation right. If the spacing is greater than a foot, the 18 inches is greater than a foot, then you're going to have to be taking less than a bar. It'll have to be less than the area of one bar. If I put them instead like 6 inches on center, right, then I've got more than one bar in there. And then you'd have, this number would reverse, right? You'd have 6. No, I'm sorry. This ratio stays exactly the same. But you'd have a smaller number down there. You'd have like 6. So that would then double the area. The area would go up. At any rate, it's good to realize where the area compared to the area of the bar is going to increase or decrease, just so you can, because you can just logically think that number should go up or go down, and pay attention to whether you're getting the equation set up, because it's easy to get this upside down. Anyway, okay, so assuming you get that, that gives you then the area per foot. D you can calculate. D is an actual distance, right? If this is placed, it has in this case a 3/4 inch cover. That would be cover for an interior slab. That's to protect the steel. D is measured to the center of these bars, and for a slab, you're always going to have bars going in both directions. But there's a primary span for a one-way slab, particularly. One-way means it's spanning in one direction. It'll have a primary strength like a beam in one direction. The steel in the other direction is just for cracking, to prevent it from thermal expansion, from people dropping things on the floor, I don't know what. So it doesn't crack so easily. And that has a minimum for slabs. It's even lower than the minimum for strength reinforcing. That, of course, you'd put on top so that the strength steel, the primary steel, is as far to the bottom as you can make it, because you've got to get this value D as big as you can have it. So it's measuring from the center of that steel up to the top of the slab, which in this case is 9.75. So there's the 9.75. That's D. Here are these other things. I mean, the density of the concrete. Oh yeah, look at that. And there's the area of the steel. So you got all the pieces. Again, now it just becomes like the other problem. You plug and chug. Just plug all those numbers in. Here's the area of the steel per foot. There's the strength in KSI. Looks like. So I've got to keep this in. These two have to agree. If I put that in KSI, this has got to be in KSI. That's 3 KSI. Then the width. This is the 1 foot strip, right? Looks kind of like this. If you look at the picture, there's a moment arm. That is the depth of the stress block. Not very deep, but it is a slab after all. The whole thing's only that deep. Then you calculate T, ASFY, AS based on that 1 foot dimension. Okay, the moment arm, we got D already. There's A, blah, blah, blah. There's the moment arm. The moment then, the strength moment's going to be that times the moment arm, TZ. So you get that. This comes out in inches right now, kip inches, and then you multiply. Multiply? No, it should be divide. Oh, this is in feet. Okay, divide by 12 and multiply by 1,000 or something. Anyway, you get in kip feet. That right there. So that's the strength, right? We probably want the capacity, though. Okay, to get the capacity, oh, here's this. I should have looked at this page. Here we already have it. This is the strength. Oh, this isn't the one I did. I was going to say my numbers don't match. That was the last one. This is the for the must be 11-inch deep slab, right? By one foot wide. So this is a 1 square. Well, it's 11 inches deep and 1 foot wide. Divided by 144. So per foot, you've got that. So that comes out in. I mean, you're taking a linear foot, and it's a 1 foot wide, right? So that's a per square foot. So that comes out to 137. You can think about that too. If this number were 12, right, then this should be 150, because that would be 12 by 12 by 12 by 12. If this would, I'm assuming it's a 12-inch length. That's kind of implicit, because I'm figuring the weight per linear foot. So there's a 12-inch length. We're using a 1 foot width. We just picked a width of 12, the 12-inch strip. If the slab were 12 inches deep, so a 12-inch deep slab per square foot weighs 150. That's the density. That is the 1 cubic foot. That is 1 cubic foot. If we had a 6-inch slab, what would it weigh? 75 maybe. If you had an 11-inch deep slab, what's it going to weigh? Less than 150, right? It would be 137 or something apparently. Okay, per linear foot, which is square foot. All right, then we put the gamma factor on it, and that gives us the factored load there. See, this is without the factor. This is with the factor. Okay, with the fact, we have to have it with the factor so we can put it into this equation. This is mu, which has the factors on it. Here, this one is the unknown in this case, but we know what that factor is. So we put those two in. This we knew, and we also know this now because we just calculated that and the phi. And the only thing you don't know then is that guy. You can solve for that. So 200 pounds per square foot would be the capacity of that. All right, well, actually, yeah, so you could do that. That first homework, if you haven't already done it, the one I pushed it back to Monday, but you could actually do it today if you had time. And then next Monday we'll go over the design equations, and that'll be due the end of the week. Okay, so.